Okay, Matt, I don't have it open, so maybe you can give me the questions, the info. So what's the story with this guy? Oh, hang on. Oh, come on.
What is the relationship between the electric field strength E at a point and the force F on a charge Q at that point?
What? That's the first question. How much is that? Half a mark?
1 mark.
1 mark. Is this A part 1?
Yes, A part 1.
Right, so the relationship is exactly this. E equals F over Q.
A part 2.
Okay.
If the charge Q is half.
Oh, this thing again. Yeah, okay. If the charge Q is halved.
What is the effect on each of these quantities?
Force is half and field is not changed.
Yeah, okay. So basically if it's like this now, so this becomes 2 F over Q. Now, the electric field strength doesn't change. That's a constant. So you could think of it like this. You know what I'll do? Okay. If these guys are supposed to be the same, because it's a constant, and if the charge is halved, then the force must be halved as well, because you can think of the formula as like this. Because E is a constant, then you get the simple relationship force is proportional to charge if you multiply across. So yeah, the answer would be F is halved and E is constant.
E is field.
Field strength, yeah. So 1 mark, 2 marks? What's the story?
2 marks.
Yeah, maybe 1 each. Okay, what's next?
B part 1.
Yeah.
B. For point charge A of positive 2.5 millicoulomb. B part 1. Determine the electric field strength at a point 2.5 cm from the charge.
Okay, so that's our formula. 1 over 4 pi epsilon 0 Q over R squared. Isn't that it? Ooh, who could this be? Seba, perhaps? Chow, even? Chow. Not Seba. Okay. Can you type that in, somebody?
Six.
10 power. Unit is newtons per coulomb. Oh, how many marks is that, Matt? 2. I think it might be the same actually as voltmeters. 2. You got it there, Matt? Or are you checking the answer?
Yes.
Which? You got it or are you checking the answer? Okay. Yeah, I wouldn't trust me either. Is it right?
Yes.
Oh, good.
B part 2. Determine the magnitude and direction of the force on a charge B of minus 1.5 millicoulomb if it were to be placed at this point.
Oh, I see. So you've got your 2.5 millicoulomb as a positive, and then what do you say? You put in negative, is it?
Yes. Negative 1.5.
1.5 millicoulombs, and the distance is the same distance of 2.5 centimeters, and they want the force? Is that it?
Determine the magnitude and direction of the force.
Okay, well let's do the direction first. So the direction is obvious because they're negative and positive. It's towards the positive. Obviously, it's an attraction, right? Yeah? Because that's negative and that's positive. Yes?
Yeah.
And we can get the force by using Coulomb's law, 1 over 4 pi epsilon 0 q1, q2, or squared. So that's 1 over 4 pi epsilon 0, 0.025 squared, 1.5 times 2.5 times 10 to the minus 6, because it's minus 3 and a minus 3. Yeah? That's okay. How many marks is that now?
3.
Is that right? Thank you, Chow, if you can.
5.4 times 10 to the power 7 meters.
10 power
7.
7. Okay. What is next?
D, 3. If positive 2.5 millicoulomb were to be added to each charge, describe what would happen to the magnitude and direction of the force on charge B.
You see, he's so lazy sometimes. So we're just doing the same thing again, except the charges are slightly different. So he said to add a 2.5 to both, was it?
Yes.
So that will make this fella a 5 millicoulomb and this fella a 1 millicoulomb? Because you add 2.5 to minus 1.5. So what has happened is that has become a positive. Now, what precisely is the question?
Describe what would happen to the magnitude and direction of the force on charge B.
Okay, so I don't think we have to necessarily calculate it, because it just says describe what would happen. So this is what I would say happened. The direction. Yeah, tell me what would happen to the direction of the force. Yeah, so describe what happened to it. You would say it reversed. And what would happen to the magnitude? Well, 1 times 5 is 5. And here, what was 1.5 times 2.5? It doesn't matter, it's less than 1 times 5, isn't it?
Yes.
So the direction of the force reversed and the magnitude increased, isn't it? Isn't it? Because the force between a 1 and a 5 is more than between a 1.5 and a 2.5. Yeah. We could even calculate it if you want. You know, you just have to change these two numbers. That's all. You know, so I could even calculate it here.
In the marks given, they calculate.
They want you to calculate it. They want you to do the exact same thing again.
Yes.
Ah. So I think is it 7.2?
Yes.
The force increased to 7.2 times 10 to the 7 newtons. Just literally change these two numbers here. That's all. How many marks?
3.
So 6 marks for doing the same thing twice, right? Okay. What's next?
Sketch the field lines and 3 equipotential lines for the electric field around a point negative charge.
Okay. Is this part 4?
Yes.
Now, did he say if it's positive or negative point?
Negative charge.
Fine. So there's a negative. So what way do the field lines look? Like this. Bigger here, but then they get a little bit smaller as you move away. How many marks for this?
And also three equipotential.
Don't you worry, I'll get those equipotential lines. So they're the field lines. And then the equipotential. So he wants 3 of them?
Yes.
Okay. There's 1. There's 2. And there's 3.
3 months.
Nice.
In among C, there's another field lines radial.
Field lines.
Radial.
What do you mean?
I don't know.
Oh, it's explaining how the marks are going, isn't it? So, does it say like 1 mark for field line radials?
Yes.
So that means 1 mark for the fact that you have them in a circle. But maybe some students have them pointing the wrong way. So they could still get that 1 mark. Like what's the other mark? Direction?
Arrows pointing towards the chart.
Yeah, okay, good. So if you were to flip these arrows around, you would get 2 out of 3. You would get the radial mark and the equi mark. Okay, what's next?
C. A particle with a charge of positive 3.2 times 10 to the power of minus 19 coulomb is projected at 2.8 times 10 to the power of 5 millis per second. Meter per second.
Yeah. Millis per second, I wouldn't even know what that is.
Into a uniform magnetic field of 35 milli
Tesla. 35?
35 milli Tesla.
Okay.
The velocity of the particle is perpendicular to the magnetic field. C part 1. Determine the magnitude of the magnetic field force on a particle.
The force. Fine. The formula for the force here is QVB. So that will be 3.2 times 10 to the minus 19 times 2.8 times 10 to the 5 times 35 times 10 to the minus 3.
What is the MT stuff?
The what?
The MT.
MT. Millitesla. Yeah. Can you type that in, Chow, please? Thank you.
Tesla is
For flux density, yeah, B. Yeah. Also the car.
how about there's one symbol like a
Weber.
or Weber, or WB.
This is why we don't do the fields question in the exam. Thank you, Chow. Pretty small, huh? Okay, what's the next part, Matt? Is this wrong?
Yeah.
It's wrong.
The Marcus Q says it's 3.14 times 10 to the minus 15.
3.2, 10 to the minus 9. Oh, I think you missed the 2.8. You missed 2.8, I think. 3.14? Yeah.
Yes.
You missed this guy. Okay, what's next?
C part 2. The particle has a mass of 3.34 times 10 to the power of minus 27 kilogram.
Okay.
Determine the acceleration of the particle.
Ah, baby stuff, because it's just F equals ma, right? So A equals F, which you know, over M, which you know. So F we know, and M is now 3.34 times 10 to the power of minus 27. So that is 9.39 times 10 to the 11 meters per second squared. Right. How many marks for that? Don't say more than 1.
1.
Oh, good. Okay, 1 mark. Fine. Now, part 3?
Determine the radius of the circular path of the charged particle.
Yeah. Now there's a formula for this. It's R equals what is it? Something over something. Actually, I'll tell you the formula.
Like a circular.
No, you can use your circular motion formula because you know okay, so you could use, right, guys, look up, there's 2 ways to do this last part. You know the A, okay? So you can say, what is it, A equals v squared over or. And you know the a and the v squared, so you can get the or. Okay, that's one way to do it. So what was the v here? What was the v, Matt?
2.8 times 10 to the power 5.
Andek, could you type that in? But there's another formula that will give you the same answer. A short. I can show you. I can tell you what it is. It's in the formula book.
Um, 0.0835.
Say again?
0.0835.
Ah, which exam is this? It should be in this one.
So is this formula in the paper?
No, there's another formula which.
Which one?
The A is equal.
There's another formula, and I saw it before. No, okay.
Yes, and then.
There's?
What are you saying, Matt?
The A equals V squared R. Is it?
What the heck? They must have forgot to put it in this version of the exam. I saw it before. It's another way to calculate the radius. I can't remember. I did it. Well, I'll tell you what I'll do. I'll prove the formula. So, you know, you have the formula A equals V squared over R. And you also have the formula A equals F over M. And F is QVB over M. So if you put them together, you get V squared over R equals QVB over M. Cancel, cancel. Or equals, that's it, MV over QB. Now this, I remember seeing this in one of the exams. I thought this was in the book. But it'll give you the same answer as that. I could have sworn I've seen that in one of the exams. Like I really remember seeing that in one of the versions of the exam. So it doesn't matter because I think in the marking scheme, if I were to guess, Matt, the marking scheme probably did it this way because they just asked you to calculate the A. Or did they use this formula?
They use the A equals B squared.
Yeah, okay, so they did it the first way.
Or approaches using R equals MV over BQ.
That's what I said. Okay. Right, what's the next part?
Determine the magnetic field required to cause the radius of the path to be reduced to half the value of
Oh, this again. So, sorry, they want the radius to be halved. So what would you have to do to make the radius half as small? What do you need to do to the B to make this guy half? So if you use R equals MV over QB, you want the R to become R over 2. What do you do to the B? Yeah. So what's a nice English way of saying that? Yeah, I know, even nicer. Double the B. Yeah? More fields? One mark?
Yes.
He loves those multiply by 2, divide by 2 questions. Because that came up twice in this one question, didn't it?
Yeah. No, wait, no.
Yeah, twice, didn't it? Because earlier, yeah, at the very beginning, he said what would happen to the E, or what would happen if you half the Q.
Is this kind of field question considered as easy?
I would consider this easy. It's not usually this easy. Anyways, what's the next one? B5, is it? B4?
Yes.
Is this waves?
Yes.
Okay. What's the story, Matt? Or no, I'll click on Andek. What's the story, Andek?
The string of a musical instrument can be modeled as below.
Is this the one where you have the two bridges
Yeah.
and there's a string here?
Yeah.
Cool. Oops.
The string is at constant tension and is prevented from moving at the two bridges.
Fine.
When the string is cut, stationary waves can be formed on the string.
Cool.
What is meant by a node? That's A1.
The node is this point here. So for A1, the node is the point on the standing wave of maximum vibration. Yes, Matt?
I think the node is the bridge.
The problem is I'm actually too warm and it's starting to affect my brain. Node, and this guy is the anti-node. Flip's sake. Right. A part 1. The node is the point on the standing wave of minimum vibration.
Can I write like a point where it's no
Yeah.
amplitude?
Yeah. You can also write it as a zero amplitude point. Yeah. Oh, I think I need a frappuccino or something. I'm hot and hungry. Don't worry, I won't take your frappuccino, Kim. It's not even a frappuccino, it's a cream something anyways. Right, A part 2, what's that?
What is meant by an antinode?
Haha! Why did you make me delete the... You could have just told me. Okay, guys, right. So it's the same, except you just replace the word minimum with
Maximum.
maximum. You guys. Alright, what's the next one?
Oh, sorry, no.
Yeah. A3, is it?
Yeah. The length of the string is 0.75 meters.
Yeah.
Determine the wavelength of the lowest frequency which can form the stationary
Okay.
wave on the string.
So, if the length is 0.75, then that means the wavelength would be 1.5, because it should be like this. So, it's fine. Next, part 4.
Determine the frequency. Wait, sorry. If the lowest frequency.
Just a sec, sorry, I might see. Oh.
If the lowest frequency which can form a stationary wave is 800 Hz, determine the speed of a wave on the string.
Alright, so you have the formula V equals lambda F. So that's 1.5 times 800. So that's 1200 meters per second. Okay. Next. V is 5.
Determine the frequency of the second harmonic of the string.
Fine, okay. So the second harmonic would look like this. So that was the first harmonic. And the second harmonic would be this, wouldn't it? Yeah, it's the second harmonic. So in this one, the wavelength is now different. It's 75. So if you recalculate V equals lambda F, basically your answer will be 600. It'll be half the size. Because the only difference is the lambda now is this instead of that. Half the size. Right. Next. Part 6, is it? Or part B?
6.
6, okay. Yeah. Did I miss something? Or? Oh! And the V is the same, is it? Yeah, okay. So, so then we have 1200 equals 0.75 F. I'm using this formula. So let's get that there. 1,600? Okay, next, Andek.
Sorry.
Yeah.
The third bridge is added in order to produce a node at the distance of 0.25 meters from the end of the string.
Okay, hang on. So that's 0.25. So then it means that this guy here must be 0.5. So it looks like this now. Cool. Okay. Go on.
The rest of the string between the bridges is still free to oscillate.
Mm-hmm.
Sketch a diagram to show the lowest frequency of stationary wave, which can now be produced on the
Okay.
full string.
So if this is a node and a node, then it must go like this. Okay. And this is 0.25, which means this must be 0.25, which is in the middle there. Which means you basically have this picture.
So they all add to 0.75.
It still adds up to 0.75, yeah. So what is the wavelength here? The wavelength would be 0.5 meters. And what did they ask you for? Just to draw it?
Yeah.
Okay.
Sorry. Yeah, with the full length of the string.
What's next? Part 7?
Yeah. A different string of length 0.75 meters with no third bridge produces a fundamental frequency at the same frequency
Hang on, say that again. A different string.
of length 0.75 meters,
Okay, still the same length, okay.
but with no third bridge.
No third bridge, okay. So we're back to this picture.
It produces the fundamental frequency of the same frequency as calculated in number 5.
In number 5, which is 1,600, okay.
What is the speed of a wave in the second string?
Again, this. V equals lambda F. So that's 0.75 times 1600. Goodness sake, this guy has no imagination when it comes to questions.
It is fundamental frequency.
Huh?
Or you said the fundamental frequency.
Yeah.
So
Hang on, maybe I'm mishearing you. Maybe I shouldn't be so harsh. Read the info to me, Matt, please.
a different string of length
Yeah.
0.75 meters
Yeah.
with no third bridge produces a fundamental frequency at the same frequency as that calculated in part 5.
So that's 1,600.
Wavelength is 1.5.
I wrote the wrong number here. Thank you, Matt. Again, I'm tired, hot, and hungry. That's 1.5. Yeah, because that's only half of a wave. Terrible, Stephen, terrible. So that's 2,400. Correct? Great. Next, Andek.
State with reason if these waves are transverse or longitudinal.
Transverse. Since the vibration is perpendicular. Perpendicular. Sorry. Because it's vibrating this way, you know, which is perpendicular. So, transverse.
Let's say that amplitude is perpendicular.
Amplitudes and I don't like it. Maybe you can, but I don't like it. Right, what's next? What part are we on now? 9? B.
Yeah.
Okay, B.
Coherent sound waves of frequency 1,500 Hz are produced from two identical speakers 1 meter apart.
Okay. 1 meter apart.
Yeah.
That's the D, and the frequency is what? 1,500.
Yeah.
Okay.
And an interference pattern is produced due to superposition of the two waves in a similar way to the Young-Slits experiment.
Yeah.
So the speed of sound in air is 330 meters per second.
Is what?
330 meters per second.
330.
Yeah.
Okay.
So question number 1 is, an observer moves along a line parallel to the line joining the two speakers,
Yeah.
but displaced from it by a distance of 20 meters.
Okay.
The observer notices the sound gets louder and quieter.
Hey, that's like my question in the workbook. You copied me.
Determine the distance between the two loud spots along the top of the line.
Just like my question. Okay, so x equals lambda d over d. Isn't that our formula? I think for the x here. I think so. We'll see if we get the right answer. V equals lambda f. So lambda equals v over f. So this would be Vd over Fd. So that is 330 times 20 over 1500 times 1. Is it 4.4?
Yes.
Okay, what's next, Andek?
Describe the effect on the loud spots if the speakers are moved to a separation of 0.5 meters.
This guy. So he wants to know.
It's half.
The D is halved. Yeah. What happens to the what?
To the loud spots, the effect.
Yeah, so what happens to the X, is it? So if this is halved, what happens to the X? You can use this formula for guidance. So what happens to the X? Come on, students. Thank you. Right, part 3. Next. Go for it, Andek.
The speaker screaming at a separation of 0.5 meters.
Yeah.
Determine the frequency required for the loud spot pattern to be returned to its original separation.
Again. So look, if this D has halved, what must we do to the F to keep everything the same? Yeah. And did they ask you to calculate it?
No. Wait.
Well, it doesn't matter because it's just going to be 3000 hertz then.
Sorry, can I just write all of it?
Yeah, no. What's the next part?
It's
Or is that it?
it's C.
It's
No, it's B5.
Okay. Right. How far back do you need me to go, Andek?
No, that's good.
That's good. Okay. Yeah? What's up, Matt? No, you can't do that. B5?
Yeah.
Okay.
I think we've done this before.
How do we end up doing B5?
Yeah, we did this.
How did we end up doing B5? What's it about?
In a nuclear reactor, energy is released due to induced fission reaction. Each reaction uses the release of 3 neutrons. Explain how a constant rate of fission can be maintained in the reactor with reference to the control load and
Are you saying we did all of E5? I have no memory of this, but you remember doing it.
You can't really do it.
Ah, no, if you haven't, no, time is precious, so if you have B5 done already, if we did it a while ago, did we? So let's just recap where we are. We're looking at 1718. We have all of version 1 done,
V5 as well.
and version 5 as well. And is there 2, 3, and 4?
Yes. We haven't done it.
Yeah, we haven't done it yet. Yeah. Like we have all 3 versions there, 2, 3, and 4. Yeah. So we'll go on to 2 now. What we'll do is you can start it now, but please, you must finish it at home.
Is it better to practice the most recent papers?
This is the most recent one, isn't it?
Yeah.
Oh, it is better to practice the most recent one, because it should likely be the same person writing the exam, the same guide. So this is why. Yeah,
So this year would be the same guy?
I think it'd be the same as this one. Yeah.
The half guy?
Yeah, I think so. The half guy. Yeah. Yeah.
If they change the guy, the whole question will be very different.
It's not supposed to be, but in real life it is. Because if you look at the past papers, you can see when they change the writer. You know, if you look at the very old papers, they're very hard. Then the papers in the middle, they're okay. Not many definitions, the calculations and the questions are straightforward, not a lot of English. Okay. Then the new guy, lots of English, lots of definitions, calculation questions kind of lame, you know. It's different style. Okay, can you get a start on section A on version 2?